Hello, I am Andrew, and I am here doing the first of two episodes, or of my episodes on the Alcubierre drive. This first one will be on how the drive itself functions, like the math of it, because, yeah. The second one will be on the problems and solutions for the drive, like the energy requirements and just general setbacks. To start off with how it works, I'll start off with who Alcubierre himself is. So Miguel Alcubierre was born on March 28th, 1964, in Mexico City. He moved to Wales in 1990 to attend the University of Wales for graduate school, which is in Cardiff, United Kingdom. He received his PhD in numerical general relativity. Then later, after research and studying all that hard work, he developed the drive in 1994. Following, I guess, three equations are all equations that he posted or published in his, I think it was 2000. When was that? No, 1994. Holy moly. His 1994 research paper on the Alcubierre drive. First of three is the general warp field mechanic, which is ds squared is equal to negative c squared dt squared plus dx minus v sub s times t times a function of r sub s times dt squared plus dy squared plus dz squared. The next equation is the function of rs that is in the general warp field mechanic, and that is the shaping function. So the shaping function is function of r sub s is equal to tan h times sigma times r sub s plus r minus tan h times sigma times r sub s minus r over 2 tan h sigma r. That function being like the shaping function just, I guess, describes and controls the general shape of the warp bubble. The next equation is the energy density. So that's like T super 0 is equal to negative 1 over 8 pi times Vs squared P squared over 4R sub S squared times df over dr sub S squared. And yeah, that equation just represents like the energy required and I guess where the energy is like the densest in the drive when it's graphed. Yeah. And the first equation, the ds squared, ds represents the space-time interval, or which is just the fancy word for the distance between two positions in space-time. Dt squared represents the change in time. C in physics generally or typically represents the speed of light, such as in like E equals mc squared, or like energy is equal to matter times the speed of light squared. So like that's the equation there is describing just like what the energy potential is of something with a given mass m. And in the equation, back to the general field matrix, I think it was, yeah, dx or sub s or dt and r sub s are the radial position of the moving space around the spacecraft. So I guess just describing the space more. And a function of r sub s, it develops into like what's called a top hat shaping function. So like if you're to graph it would quite literally start to look like a top hat. And in the function of r sub s, you might be thinking, why on earth is this dude saying sigma in a podcast about faster than light travel? That's because sigma is a Greek letter, and that Greek letter in physics, I guess not in this specific equation, sigma represents the wall thickness. And then r represents the radius. The higher the number of sigma, the thinner the wall will be of the drive. So another thing with having the walls thin, though, is thinner the wall, the greater the York time will be. Not New York time, just York time. So the higher the York time, the um, I guess if you're to look at like the graph in the background of this video, the higher York time would make like the blue area higher and the red area lower. I guess stretch those places. So if you're to make it thinner, it would also make it taller or shorter, depending on if it's the contracting or expanding space. And York time, I guess, is just a parameter that describes the expansion or contraction of space. I guess that's the shaping function pretty meh described. And energy density mainly uses variables that I've already just now described, so that's fine. But these equations are equations that Alcubierre, I guess, yeah, he published that, but they were described pretty well in the research paper. It's not really as much of a research paper, but I guess research findings from NASA, their project that EagleWorks did, ran by Dr. White Sony, or Sony White. And that article is named Warp Field Mechanics 101, published in 2011. But that's a summary of a large project they did where they went and experimented trying to see if warp travel or the Alcubierre was a plausible, I guess, possibility. But to test that, they ended up developing their own tools, such as the what is a device that shoots hydrogen neon beams to measure the fluctuations in the space that the Alcubierre drive would form. So, like, they were testing to see if it's possible, and they were measuring it. But, that device was called a interferometer. It, just a pretty neat device that they use for measuring that stuff. That article also summarizes other stuff. It's like the main source other than Alcubierre's research article that he posted himself that I used for information for this. So don't worry, most of I guess the information I'm saying is correct as far as science knows. But the the Alcubierre drive is like it essentially compresses the space in front of you and expands it behind you. So it's like pushing you through space, or as Alcubierre described it, like riding a wave. I personally prefer to think of it as like I guess as a bubble, which is how it's commonly described. But I think that's also kind of a misleading term, since it's not physically putting you in a bubble, but rather just pushing you like a wave. But decent way to think about like why it works would be like to imagine you're holding like a bubble, like an airtight bubble. Air inside is stuck there, and say you like taped or glued a Lego figure inside of it, and you throw the ball. The Lego figure, from its our point of view, it doesn't know it's moving. The air around it isn't moving around it. It's just kind of sitting there. It's pretty much the same with the Alcubierre drives. Like, no matter how fast you throw the ball, the minifigure cannot move faster than, I guess, in this case, since it's air I'm referring it to, the Lego figure cannot move faster than the speed of sound or break the sound barrier, since it's not moving fast enough in relative to the air around it. For the same, or for that same reasoning, the Alcubierre drive cannot break the speed of light, since it's not moving faster than the speed of light around it. So, I the Alcubierre drive moves a solid flat area of space. Is flat in terms like if you're to look at a graph like the one in the background of this video. It moves that through space, so you're sitting still in space. So when it accelerates, you don't feel acceleration. When it decelerates, you don't feel deceleration. But also because of this, it allows you to accelerate pretty near instantly. So you don't have to spend 5 days accelerating to 10 times the speed of light. Although that does use a ton of energy, but that's for the next episode. But another great thing about this drive is that, like, unlike the FTL travel that's typically thought of in the traditional sense, since it's not traveling, or since the spacecraft is not traveling through space itself, like faster than the speed of light, it cannot break causality, since it's not time traveling that faster than light travel typically would cause, I believe. Then, because of this is one issue that FTL travel, when described, will commonly have. They're like, oh, but that'll cause time travel. That's only if you move through space faster than the speed of light, which we're not worrying about here. But, and I guess another visual representation of how the drive would work, like similar to, like, I guess not similar, different than how like the bubble and wave work. Another one I found was like a spring. I think of the Alcubierre like a spring, like that. So it's pulling the space in front of it closer and pushing the space behind it backwards. I personally don't like this one as much because it just, in my mind, it doesn't make as much sense. In yours, maybe it does. I don't know. It depends on who's listening. But there's, let's see, there's like many uses for this as well. So like, as you can probably imagine, if you're trying to, say, travel to, let's say, the nearest habitable solar system, I guess, Alpha Centauri, that solar system is 4.3 light years away. So if you were to make a ship that is traveling, I'll just say 99% of the speed of light, assuming we have the ability to get that fast, will still take you like a little over 4.3 to reach. With the Alcubierre drive, you can reach there in how little time you want without, I guess, breaking any laws of physics. But then, I guess, along with that, the faster you want to travel, the more energy you use. But again, that's something I'll have to describe in the next video or the next podcast. And I guess one way to cut down on the power would be to take advantage of the fact that the York time doesn't necessarily influence speed, but rather just the or no, it would be the wall thickness that would influence that. The wall thickness doesn't influence speed, but it influences how much room is on the inside of it. So if you want like thicker walls, you might travel a little slower, but you use a lot less. No, you won't travel slower. You might have a little less room, but it'll save a lot of energy, which is a massive problem. Like, um, the biggest issue with the drive isn't trying to figure out how to make it. It's trying to figure out how to store, how to use, and how to obtain the amount of energy required for it. Like, um, I believe for 1 second of travel with the Alcubierre drive, I calculated that you would need. I guess I didn't do it. I had help from Google, but about 1 second of travel with the Alcubierre drive would, or according to Alcubierre's original estimate, would be 17 quadradecillion joules. A lot more than we have access to. So yeah, that's just a touch on what I'll describe in the next video, but I don't want to go too far into that. That's stuff for another video and stuff that doesn't belong in this one. I believe that is as much as I can describe in about it in simple terms as I can put faster than light travel. So that will be, I guess, the end of this initial podcast or video, whatever you want to call it. And I hope I'll see you in the next one. Godspeed.